All right. So, what we've done this semester is we have learned about our place in the universe and how we study the universe, in particular the solar system. So, we've learned about planets and asteroids and comets and the moons and everything that's in our solar system. And then we discovered how solar systems are formed. And now you know that there are thousands of solar systems that we know of so far in our exploration of the universe. So, to wrap up the semester, we want to discuss exploration and life in the universe, including what is the current status of space exploration, where do we search for life in our own solar system, and how do we search for it, and where and how do we search for life outside of our solar system. So, there's a couple of different ways that we currently do robotic space travel. One type of mission is something called a flyby mission, which is cost effective because um, you basically just launch a rocket with a spacecraft on it, get it going really fast so that it reaches its destination quickly, and then they take pictures and keep on going, or they do their science, take pictures, get magnetic field data, get gravitational field data, whatever we've put on the spacecraft, but they just get one opportunity at their primary target. Then there are orbiters, which are great because you get more prolonged observations because these are spacecraft that go to a target, then go into orbit around it. And so you get dedicated observations of a target object. You tend to minimize cost and save time by using things called gravitational slingshots and aerobraking. So if we want to send a spacecraft to Mercury, sometimes we aim it at the planet Venus first and use Venus's gravity to speed up the spacecraft and change its trajectory. That would be a gravitational slingshot and aerobraking. And then what we've done a lot for Mars in particular are landers and probes. We have landed a robotic spacecraft on the moon, on Venus, on uh, Mars in particular, and then a couple of other spacecraft on certain moons of the solar system. But this is an image of the Curiosity rover on Mars. The great thing about these sorts of spacecraft missions is that you can get direct measurements by landing on a world or flying into its atmosphere. Terrestrial type worlds allow for rovers to actually land and then explore, which is why we see the wheels here on Curiosity as it's roaming around a region of Mars. And so the Mars rovers, in particular, like Curiosity is basically a traveling science lab the size of an SUV roaming around Mars. Now, sample return missions are becoming more common, in particular to asteroids. And so the Hayabusa 2 spacecraft that went to the asteroid Ryugu is actually returning samples to Earth in December of 2020. And then the OSIRIS-REx spacecraft mission just recently in the fall of 2020 got collected samples of the asteroid Bennu, and we'll be returning those samples in a few years to Earth as well. And so this gives you the benefits of having a lander on a world, but then you get access to Earth scientific facilities to analyze the data. And these types of missions are ongoing. So, this is a recent roundup of solar system missions from here in December of 2020. And you can see the ones that are listed in orbits around their objects. They are currently ongoing, and then you'll see a list of upcoming events here, including uh, China's Chang'e 5 lander reaching the moon here in the first week of December 2020. So, all sorts of exciting stuff going on in our exploration of the solar system. How about outside the solar system? Well, traveling outside the solar system is something called interstellar travel, travel in between the stars. And we have launched some spacecraft that have explored in our solar system, but because they were flyby missions, they just kept going. So, for example, Pioneer 10, which was launched in the 1970s with this sort of message on it, this graphic message that you can see for anyone who might come across the spacecraft in the future. It's just keeping going, but it will not come closer than 3.3 light years from any star for roughly 2 million years. So, at the rate at which it's traveling, it's not going to be reaching another star system anytime soon. So, let's talk about the way space travel is currently done. The physics of space travel really started back with Newton's laws. And as I like to put it, and this, I know this insults some people, but as I like to put it, we've known the physics of rockets for a long time, and then the engineers had to catch up and build them. Rockets developed rapidly during and after World War II, leading up to the launch of Sputnik in 1957 by the former Soviet Union. And the physics of rockets really hasn't changed much since. The type of rockets we use are still pretty much the same as the ones that were developed in the mid 20th century. So we're talking about chemical rocket propulsion for the most part. And then what are some limitations on space travel? Well, Einstein's theory of special relativity limits the velocity of any object in space to less than the speed of light. And so until we can figure out some way to break the speed of light or increase in efficiency of energy production, interstellar travel on human timescales remains out of reach. So this is an image of the Millennium Falcon from Star Wars, where you just pull a lever and you travel in the hyperspace and you end up somewhere else really quick, and that's just not feasible currently. The current primary limiting factor in rockets is something called the mass ratio, which is basically how much mass is the rocket carrying before and after the fuel it's burned. A lot of the weight of getting a rocket off the ground is actually the weight of the fuel that's needed to boost it. We have what we call single stage rockets, where you just have one, the rocket and the spacecraft are all one object. And that means the weight is all tied together, and that's actually really impractical for reaching Earth's escape velocity. So, what we tend to have when we launch a spacecraft are multi stage rockets. And then, as stages are used, like they use up the fuel, you discard that part of the rocket that has the fuel. So, this is an image from Apollo 6, which was one of our early missions trying to figure out if we could get to the moon, launching one of its stages away after after the spacecraft had achieved Earth orbit. Um, and so by discarding the overall rocket weight, you can actually increase your speed. But to reach even faster speeds, more efficient fuels are needed. And by more efficient fuels, we mean the mass of the fuel would in and of itself be less. So, what are some ideas here? There are things called ion drives, which are low power, high efficiency alternatives to chemical rockets. What they do is basically they have a source that produces ions that throws it out the back of the rocket to propel you going forward. You can't actually use these. These are not powerful enough to help you escape the Earth, but once you're in orbit, the low power thrust that they produce can actually achieve high velocities, up to a few percent of the speed of light. The Dawn spacecraft mission that went to the asteroids Vesta and Ceres is an example of a spacecraft that was operated by an ion drive. Another experimental design is something called a solar sail, where catching solar radiation provides a momentum to give the spacecraft a boost. And so it would be another case where it'd be very low power, but with enough time could achieve high speeds. So what this is an image of is of a project called Light Sail by the Planetary Society. This is an actual image of where they deployed a very, very large sail in orbit around the Earth to catch sunlight to see if they could actually get the spacecraft to move. And they did. So this was just an experiment. There's been no spacecraft missions to other worlds using this sort of technology yet. A very science fictional idea, as you can see here from Star Trek, is the idea of people going into suspended hibernation, or where you freeze the people or otherwise slow down the metabolism of the body until so that you don't age, you don't need to eat. You're basically going to deep sleep for decades or centuries, and you would only awaken the crew when they reach its destination. Basically, you would have to um, have a spaceship on autopilot, and then where everything would turn on when needed. Now, this is way, way, way beyond our current scientific capabilities, but it's a fun science fictional idea of how space travel could be achieved. Um, Probably the most practical way to do interstellar travel would be something called a generation ship, where the people who start off on the spacecraft mission are not the people who arrive at the destination, that multiple generations of humans would be born and then die on this long voyage to whatever destination they would have. This is a spacecraft called the Nauvoo from the Expanse television series here, which was designed to be a generation ship. Is this currently within our reach? No, but it is, and then once again, an interesting idea. And right now, without breaking the speed of light, probably the only way that we would get to, that humanity would get to another star system. Unless we can start going really, 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 really fast. And then we start dealing with some other interesting things that happen. So, time dilation is a consequence of special relativity. It says that when you travel close to the speed of light, the person who is traveling experiences time more slowly than a person who, say, would remain behind here on the Earth. So the table here is called round trip travel time to the star Vega, which is the brightest star up in the constellation Lyra. And the speed in the left hand column, the little letter C there means the speed of light. So we have 0.1 c would be 10% the speed of light, for example. So whereas if you're going really, really, really slow, at like that top speed that we have, um, you would take a million years to get to the spacecraft. And because the spacecraft would be moving slowly, a million years would also have passed for the person here on Earth. But as you go closer and closer to the speed of light, the time measured on by the person on the ship becomes less and less compared to the time measured by the person on Earth. Now, um, this this is one of those things that you might have heard of called the twin paradox. How is it that two people born on the same day at the same time can have different ages? Which is if one travels close to the speed of light and the other one is left behind. Now, this phenomenon then could allow humans, if we could travel really, really fast, close to the speed of light, the human on the spaceship would be able to travel to distant stars uh, within their lifetime. But the person, the people back behind on Earth, wouldn't be able to gain the benefits of their new knowledge. So, for example, our Milky Way galaxy that we live in is approximately 100,000 light years across. Someone could get across the Milky Way, say, in just 22 years, but back to the people here on Earth, it would have taken more than 100,000 years. So, any information that a scientist on that spaceship would find out couldn't even be communicated effectively back to us here on Earth. So, if you're going really, really close to the speed of light, a trip to the Andromeda Galaxy, pictured here, which is 2.5 million light years away from us, you could go there and back in 60 years if we could possibly get close to the speed of light. But 5 million years will have passed here on Earth. So, the benefits that the people on the spacecraft would get wouldn't help out humanity. And so I'm the sort of person who thinks that individual accomplishments are not more important than the accomplishments as a whole. And so I would find it weird to put effort into space travel that only benefited the people on the spacecraft. Call me weird. So, um, but even if we wanted to achieve that as a goal, we would need much more efficient fuel than we have currently. And the only fuel that we can think of that would be 100% energy efficient would be matter antimatter annihilation, where matter and antimatter collide and all of the mass get converted to energy via E equals mc squared. But this isn't really a practical option because we barely produce any antimatter here at all on Earth. So, if this is to be possible, it can't be done by current technology. Um, Another interesting idea is something called an interstellar ramjet, where you actually don't have fuel with you. You pick up fuel as you go. So you have this huge scoop in front of the spacecraft, and it scoops up the hydrogen that's out there in the interstellar medium, and then it ejects it out the back to provide thrust. The problem is with this is that space is really, really empty, so you would need a huge scoop. Some estimates are like your scoop would have to be as big as the moon. And then also on a more practical scale, um, if your spacecraft is going fast through space and you start running into things, any slow moving particle in space becomes a high speed particle to the travelers and therefore quite lethal. So that's another thing we would have to worry about is running into particles out in space with our spacecraft going at high speeds. So uh, if you are a fan of science fiction, usually you hear words like hyperspace or warp speed as a way to say you can spacecraft can travel in between worlds in a reasonable amount of time. So where do those ideas come from? The Einstein's general theory of relativity proposed the idea of space-time, which is that space is actually a four-dimensional fabric, where the fourth dimension is time. And if you could somehow stretch and deform space-time, such as by something called a black hole or a wormhole, you could get a shortcut. So, for example, here we have the Earth being 25 light years from the star Vega in real space. But if we could somehow connect the two via hyperspace or warp in space-time through a wormhole, the distance between the two wormholes would be much shorter, and so we could get there faster. Um, that is the concept of a warp drive. The idea of a warp drive is that it would deform the local space-time into a wave, and then the space-time itself is what is curving and helping the spacecraft move. Can we do this? No. Will we ever be able to do this? Who knows? Is it fun to think about? Definitely. And so those are the limitations of interstellar travel. We are currently traveling throughout the solar system with robotic spacecraft with no crews on them, no people are on them. As soon as you add people, you have a lot more constraints because the human body can only undergo so much acceleration. You need to make sure there's food and water and so on. So, exploration of the universe with people outside of our solar system is very difficult to do. Is there life elsewhere in the universe? Well, we know that there's life in our solar system because we're having this conversation. We know that life exists at least in one world in our solar system, which is the Earth. How do we search for life elsewhere? This is an image of the Very Large Array Radio Telescope Observatory in Socorro, New Mexico. Um, the way we currently look for life elsewhere, there's a couple different ways, but the most common is to look for signals of other civilizations, such as radio signals or other telltale signatures of intelligent life out in the universe. Because the universe is vast and it's old, it's currently thought to be infinite in size, and where our current observations have allowed us to see out to billions upon billions of light years. And we estimate the current age of the universe is that it's about 13.5 billion years old. One of the guiding principles to understand the universe is that we think the same physical laws that operate on Earth operate throughout the universe, and that the laws of nature are constant throughout the universe. So the physics that we figure out here for how life works and for how rockets work would be the same throughout the universe. And that's just an assumption we have to make. Otherwise, it's hard to contemplate understanding anywhere else. Now, when we understand what makes up life here on Earth and then we look for it out in space, what we find out is that the elements of life are widespread and that the building blocks of life on Earth we find everywhere throughout the universe, and most specifically in those dark nebulae that solar systems form out of. So when we talk about life on Earth or life as we know it, we're talking about primarily carbon-based life, where carbon in our body and in the molecules and atoms that make up our body behave in a certain way to make bonds with other materials. Um, and so the most common elements needed for life here on Earth are carbon and hydrogen and oxygen and nitrogen. Now, could life have a different building block other than the carbon? Well, silicon is chemically similar, but silicon bonds are weaker than carbon bonds. Silicon usually only forms single bonds, not double bonds, which limits how it behaves in molecules. And silicon is 1,000 times as abundant as carbon in the Earth's crust. And so the fact that life is carbon based means that since there was more silicon available, but carbon won, then maybe carbon is more necessary than silicon for life. But carbon then is something that we would look for to try to see if there's life out there where life is defined as life as we understand it here on Earth. Another thing that seems to be crucial for life as we know it is water. Evidence points to water as a strong test then for a possibility of life. Can we look for water elsewhere in the universe? And we do see water molecules commonly out in interstellar clouds. But as you've noticed as we've traveled through the solar system, liquid water isn't common on the surfaces of worlds. The Earth is the only world in the solar system where liquid water is constant on the surface, even though we've seen evidence for water underneath the surface of some of the moons in our solar system. What roles does water play currently in our understanding of life as we know it? Water plays a role in metabolic reactions within cells. And then life depends on those metabolic reactions. Therefore, water tends to limit conditions where life exists. Life here on Earth tends to be in places where it's neither too hot or too cold for liquid water. Now, life on Earth can use a variety of different energy sources, but liquid water seems to be the one thing that no organism on Earth can truly survive for long periods of time without. So then, if we want to take a look for places where life can exist, then we're going to. Because water is so important then for life as we know it, then we define what's called the habitable zone around a star as the range of distances from a star in which worlds like the Earth could exist. And what we specifically mean by that is a region where a world could have liquid water on the surface and have it be stable. Existing within a star's habitable zone just isn't enough. As you know, the moon is right next to us and it doesn't have liquid water stable on the surface because its gravity is too low for it to sustain an atmosphere. So, there are obviously other things that come into play other than just distance from the star, but distance from the star is where we start. And then habitable zones can actually move because stars brighten as they age, therefore putting out more energy, causing habitable zones to change by moving outward from a star as a function of time. So let's take a look at some graphics that show this. So here's a case where we have a star like the sun, and the reddish region around the star would be where it would be too hot for liquid water to be stable. Too far away was labeled outside the green, so that's too cold. And then the green is just right. Sometimes this is referred to as the Goldilocks zone as well, where the temperature isn't too hot or too cold, but just right for liquid water to be stable. And you'll notice that we're assuming a planet would be a terrestrial planet about 1 to 2 times the size of the Earth in this case. Now, how does this change around different stars of different temperatures? So, remember from way back when we were talking about how the color of a star is relevant to its temperature, a blue star is a hot star, so its habitable zone would be further out from the star. A red star is cooler than the sun, so it would be closer. So, distance is definitely dependent on the temperature of the star. And then as we can see here, here's where our solar system, the inner part of our solar system, where the not the habitable planets, the terrestrial planets are. And you can see that Earth is the only planet that is definitely within the habitable zone. And we'll call that a conservative estimate, the darker green of where the habitable zone is around the sun. Some estimates say that if the the ones shaded in as the optimistic estimate make the habitable zone a little bit broader, and so Venus is still just inside of it, but Mars orbit um, could fall inside of it. And we do see evidence, as you remember from when we were talking about Mars, that the planet did have liquid water on the surface for a short period early on in its history. And then the graphic here on the right shows distance from the sun as a function of the age of the sun. And right now we're where that dashed vertical line is. That's the present. But as the sun ages and gets warmer as time goes on, by the end of the sun's normal lifetime, the Earth will actually be still kind of not so much within the habitable zone. It'll be too hot here for life unless we're in that more optimistic estimate. But Mars would fall within the habitable zone of the sun. So that's what we mean by the way as a star ages with time and it gets brighter, and its temperature changes and it gets brighter. We can see different places where the habitable zone is. So the habitable zone does change as a function of time. And then here we are with massive star on the vertical axis and distance from the star on the horizontal axis. And you can see how mass relates to temperature by showing small red cool stars and then larger blue hot stars. And then you can see how the distance from the star is affected by the temperature and mass of that particular star. So you might be wondering then, if there is only a small region uh, around a star where liquid water can be stable on the surface, where we could find possibly planets with life as we know it. We found thousands of solar systems. Do any of them have planets in their habitable zones? And so this is a graphic made um, by the Planetary Habitation Lab, and which is housed at the University of Puerto Rico in Arecibo. So here are the list of potentially habitable exoplanets with the planets of our solar system to scale over on the right. And then any of the images shown on the left are artist representations. And you might notice that a couple of them look like Earth, like they might have water on them because they have those planets are the ones that have a combination of distance from their star and size that mean that they might be terrestrial planets. So we have discovered some potentially habitable exoplanets, but not a whole lot, not yet. Because remember, the smaller planets like the Earth are the harder ones to find. So, how do we go about looking for life in the universe, especially if we cannot travel there easily with spacecraft? Well, we're going to want to be able to look for it from a distance. So, one of the ways that we do it is when we do study these exoplanets, we are trying to take a look at the spectra of their atmosphere and figure out the atmospheric temperature and composition. In particular, what we would really like to be able to detect is oxygen, because as you recall from our study of the Earth, we are in a primarily nitrogen oxygen atmosphere, but the other terrestrial planets, well, Mercury doesn't have an atmosphere, but Venus and Mars, their atmospheres are primarily carbon dioxide. And we said back at the time that the amount of oxygen in our atmosphere is likely due to biological processes. It's one of the reasons why our atmosphere is so different than the other atmospheres in the solar system. So, one thing that astronomers are looking for when we do detect planetary atmospheres of exoplanets is oxygen. Because if we find oxygen in those, like large amounts, then that could be an indicative sign of life. And then, what are some other criteria to hold life? Well, a world would have to have a mostly circular orbit. And why do I say that? Well, because we don't want really dramatic differences in temperature over the course of the seasons. So, for example, we have seasons, right, here on Earth, and we're tilted at about 23.5 degrees. But the seasons in the northern hemisphere and the southern hemisphere, they follow similar temperature changes. But if we had a wildly different elliptical orbit, say where we got much closer to the sun at one part of the year and then much further away at the other part of the year, then the seasonal variations would be drastically different and maybe not as hospitable for life to evolve. Another thing that a world would need to have to hold life would that it would be need to be large enough to retain its internal heat for billions of years, driving the motions of a living world. Because some of the places where life first evolved here on Earth, and where life still exists today, have uh, associations with geothermal activity. So, what's the probability of life out there in the universe? Well, don't worry about memorizing this, but I wanted to introduce you to the concept of the Drake equation, which was developed by an astronomer named Frank Drake, trying to calculate the probability of life existing out in the universe. So he said that in the number of civilizations out there in the universe would be equal to our star, the average rate of star formation in the galaxy, Fp times Fp, which would be the fraction of those stars that have planets. Ne would be the number of planets that could potentially hold life per star. F, F, Fl, the fraction of planets that actually develop life. Fi, the fraction of planets that have life that form civilizations. Fc, the fraction of civilizations with technology that produce signals. And then L, the length of time for which civilizations can release those detectable signals into space. Does that have a lot of basis in science? Well, it's hard to know any of those numbers, or actually all of those numbers. Which ones do we have an idea of? Well, we do actually have an idea of star formation rate, so that our star is one that we have a handle on. FP, we're starting to get a better idea of the fraction of stars that have planets, and that turns out to be a big fraction. The other things on here, though, the length of time for which civilizations can release detectable signals into space, we don't have good scientific basis for truly understanding that number. The fraction of civilizations that develop technology that releases detectable signals, we don't have. I mean, we're the only planet that we know of so far that have civilizations on it, so it's really hard to get good values when your statistics is based on one data point. But the reason why I show this to you is that people who study life in the universe do use this equation to try to develop a probability. It's fun to think about the sorts of things that need to come into play for us to search for life in the universe because it is, as you've seen, the universe is very big and we are very small and we can't get out there easily to study everything. So we're going to need life in the universe to help us out by kind of waving at us and letting us know it's there. So are we alone? Well, there's something called the Fermi paradox, which is the conflict between the two following facts. Probability and scale favors life in the universe. We are one planet in one solar system in a galaxy that has a couple of 100 billion stars in it. So that might make life sound rare. But there's billions of galaxies, so even if every galaxy only had one planet that had life on it, that would mean billions of planets with life on it out there in the universe. So probability and scale does favor life in the universe existing elsewhere. However, that's in conflict with the fact that we actually haven't seen evidence of life in the universe elsewhere so far, and we are looking for it. You might remember this is an image of Mars that I showed you earlier on in the semester, and it's basically a square centimeter of soil on Mars. Because when we do send these rovers to Mars, we're not just looking for life in terms of whether or not we see oxygen in the atmosphere or palm trees on the surface. We're actually looking for evidence of it in the soil, even. So we have been searching, and we haven't found evidence of life in our own solar system other than on the Earth so far. And then, as you know from looking out into the universe as we've done together this semester, if we can't find it here on Earth, in some ways that makes it even harder to find it elsewhere. So, this is the Fermi paradox. Life should be abundant, but we don't see it. And so the question is then, are we alone? Well, there are possible solutions to the Fermi paradox. We are alone. Maybe life doesn't exist anywhere else in the universe, which low probability, right? other life exists, but it has not yet traveled into the cosmos. And that one, I think, as you could see from our discussion earlier on in this chapter, makes a whole lot of sense because space is big and we are small, and and it's hard to travel through the universe to visit other places. And then another possible solution to the Fermi paradox is that life is so common it's boring. Like maybe no one's coming to visit us because we're just so boring to them that they don't even care to come say hi. I always find this an interesting and amusing option. And I bring up here the prime directive. If any of you are Star Trek fans, you know that the prime directive is an idea where you have a civilization that does have space travel, uh, but they don't interfere with civilizations that are not at their level yet. They just observe them from a distance so as to not interfere with their evolution. That's also an interesting idea. But I don't have an answer for you. My gut instinct is that other life exists, yet we just haven't found it. Because if I were to take the chemical elements that we see out in space and show it to my colleagues up in the biology department, they would definitely say, oh, yes, those are all the ingredients that you need for life out there. So I'm still hoping someday that we will find evidence for life in the universe so that we will know definitively that we're not alone.